We've been thinking about vectors since the beginning, but now we'll think about them a little bit more. In particular, what does a component of a vector tell you? What does a component mean? Well, just imagine some little bug that could move around on this blackboard, move around on a two-dimensional plane, and to identify all the locations on the plane, we set up an XY coordinate system. So each point on this plane, each point on this blackboard has its own distinct value of X and Y. And let's say the bug starts here and then eventually ends up here. So we can think of a displacement. A displacement is a vector that points directly from the starting point directly at the ending point. And the magnitude of a displacement vector is just the distance between the starting point and the ending point. That much we know already. But now we can think of this displacement as a sum of two other displacements that we'll call the components of D. We can think of this displacement from here to here as this much horizontal displacement plus this much vertical displacement. And the horizontal displacement we call the X component of the displacement, and the vertical displacement we call the vertical component or the Y component of the displacement. And the two components, dx and dy, are connected tail to tip because adding the X component and the Y component together gives you the vector itself. Dx plus dy equals the vector D. Let's do another example. Let's say the bug starts here and eventually gets here. So the displacement that takes you from the start to the finish is represented by this arrow right here. And you could think of a displacement from here to here as this much horizontal displacement, this much displacement along the x-axis, plus this much displacement along the y-axis. But of course, going from here to here, that's a displacement in the negative x direction, so the actual value of this x component of displacement will be negative. And then moving from here to here, again, that's in the negative y direction. So the value of dy, the value of the y component of d, will also be negative. Moral of the story is you need to pay close attention to the signs of components of vectors. Now, look at this picture and we see something. In both pictures, the vector itself is represented by the hypotenuse of a right triangle, and the two components are represented by the two perpendicular sides in that right triangle. And there's an idea that you should keep in mind. The relationship between components and the vector itself is exactly the same as the relationship between the perpendicular sides and the hypotenuse in a right triangle. Hypotenuse corresponds to the vector itself. The perpendicular sides correspond to the components. And the lengths of the perpendicular sides correspond to the magnitudes of the components, and the length of the hypotenuse corresponds to the magnitude of the vector itself. Now, this actually allows us to do a little bit of trigonometry, useful trigonometry, because one way of defining trigonometric functions is to define them as ratios of lengths of sides in a right triangle. For example, here's our triangle, and let's pay attention to this angle here. We'll call it theta degrees. And we label the three sides. This is called, of course, hypotenuse. OP for opposite, because this side is opposite to the angle that we're paying attention to. And the length of this side we call AD for adjacent, because this side is adjacent to the angle that we're paying attention to. And the trigonometric function cosine is defined as a ratio of lengths of sides in this triangle. Specifically, it's a ratio of the length of the adjacent side over the hypotenuse. Length of the adjacent side divided by the hypotenuse. And if you just do a little bit of algebra here, multiply both sides by hypotenuse, this equation tells you that the length of the adjacent side is simply equal to the length of the hypotenuse times cosine of that angle theta. And similarly, when we define the trigonometric function sine in terms of lengths in a triangle, sine is defined as the length of the side opposite divided by the length of the hypotenuse. Sine of this angle is equal to length of the hypotenuse divided by length of this side. And again, if you multiply this equation by hypotenuse, you find that the length of the opposite side is simply the length of the hypotenuse times sine of that angle. And these are two rules that we can use to figure out things about a vector and its components. So looking at one example, here it is. Let's say we have a velocity vector that points this way, and the magnitude of that velocity vector, the speed that it corresponds to, is 10 meters per second. And let's say that this velocity vector is pointing 60 degrees away from a horizontal line. That is, if you point in this way and then rotate 60 degrees clockwise, you're now pointing in the direction of the velocity vector. So the angle that tells you the direction and the magnitude, the size of the vector, that's enough information to figure out the components by using these trigonometry rules. So there's the vector, and we can think of that vector as a sum of some velocity this way, that's the x component of the velocity, plus some velocity this way, that's the y component of the velocity. And then we can use trigonometry to figure out what the values of vy and vx actually are by using these rules here. So I'll get a little space by erasing some things, but I don't want to erase that. So, 60-degree angle. Vx. The magnitude of a component just corresponds to the length of the triangle that represents the vector and its components. And the magnitude of Vx is just the length of the side that's adjacent to the 60-degree angle. In other words, length of the side that's adjacent to the 60-degree angle, this thing here is the magnitude of Vx. And so it's simply going to be equal to the magnitude of the hypotenuse, 10 meters per second, times cosine of the angle, cosine 60 degrees. And then when you ask your calculator what the cosine of 60 degrees is, your calculator will tell you that cosine of 60 degrees is 1/2. So the magnitude of Vx, the size, the absolute value of Vx is 5 meters per second. But of course, Vx represents some velocity pointing in the negative x direction. We're using a coordinate system where positive x is to the right, negative x is to the left, positive y is up, and negative y is down. So the magnitude of Vx, just corresponding to the length of this side in the triangle, is 5, but the actual value of Vx, the x component of the velocity, is really -5. Okay, now for the figuring out the y component. The magnitude of the y component of v corresponds to the length of this side of the triangle, but the length of this side of the triangle is just the length of the opposite side, which is equal to hypotenuse times sine. Magnitude of the y component is just the length of the opposite side, so it's going to be equal to the magnitude of the hypotenuse times sine. Magnitude of the hypotenuse is 10 meters per second, sine 60 degrees. And then when you ask your calculator what the sine of 60 degrees is, it'll tell you that it's about 0.87, so the magnitude of Vy comes out to about 8.7 meters per second, but Vy is pointing in the positive direction, the positive y direction, so Vy itself is positive. This is not just the magnitude of Vy, this is Vy itself. So that's an example. We use cosines and sines to figure out the sizes of the components if we know the size of the vector itself and the angle that tells us its direction. Let's flip that the other way around. What if we know the components? From that, we can actually figure out the magnitude of the vector itself and the direction angle. So let's see how that looks. So let's say we have a vector like whose components are like this. Oh, what the heck? Okay, a vector whose components are like this. The x component, say it's a displacement again, so here's the x component of this displacement. And let's say we know that it is minus 5 meters. A displacement like this means you move in the negative direction, and the end point of this displacement is 5 meters away from the starting point. And then, if you add to it some displacement in the y direction, in the negative y direction to be precise, and let's say the value of that is minus 4 meters, then adding those two displacements, displacement to the left plus displacement down, you get a net displacement from here was the starting point, to here was the end point. So the net displacement just takes you from here to here. The net displacement, d, is just the sum of its components, dx and dy. But these are the only two numbers that we know, but that's enough to figure out what is the magnitude of d itself and in what direction it's pointing. First, the magnitude. Well, it's a right triangle, and the magnitude of the vector itself always corresponds to the length of the hypotenuse that we always draw when we're showing how components are related to the vector itself. The magnitude of d just corresponds to the length of the hypotenuse, and we know the Pythagorean theorem, the square of the length of the hypotenuse is equal to a sum of the squares of the other two sides. That is, the magnitude of dx is the length of this side, and so if you square that, and then add to it the square of the length of this side, you get the square of the square of the magnitude of the displacement itself. And then if you want the magnitude of the displacement itself, just take the square root of everything. Square root of this is obviously just magnitude of d, size of d. It's a displacement, so that means the distance from the starting point to the ending point, and that's equal to the square root of the right-hand side. Square root of the square of the x component's magnitude plus square of the y component's magnitude. And in this case, dx was minus 5, so dx squared will be 25. Dx is 5 meters, so dx squared is 25 meters squared. Plus dy was minus 4, so minus 4 meters squared is 16 square meters. So that's equal to the square root of 41 square meters, and when you take the square root of that, you come up with about 6.4 meters. The magnitude of that displacement is about 6.4 meters. The size of this displacement vector is about 6.4 meters. The distance from the starting point to the finishing point is 6.4 meters. Now, what about an angle that will show us the direction? Well, for that, we need to use one more trigonometric function that we haven't thought about yet, tangent. Let's see how that works. Whenever we have a right triangle, let's say this is the angle that we're focusing on. So this is the side that's opposite that angle. This is the side that's adjacent to that angle. And here, of course, is the hypotenuse. We define tangent of this angle as another ratio of lengths of sides in that triangle. Specifically, tangent of the angle theta is just a ratio of the length of the opposite side divided by length of the adjacent side. That's tangent theta. So, if this is our triangle that relates the two components of D to D itself, the lengths of the sides in that triangle are the magnitude of D, which is 5 meters, and then the magnitude of the y component, which is 4 meters. And there's D itself. We just figured out that D is equal to 6.4 meters, or the magnitude of D is 6.4 meters. And here's the angle here's an angle that we can use to figure out the direction of displacement D. Call that angle theta, and then use our definition of tangent. In this case, tangent of the angle is equal to the length of the opposite side divided by length of the adjacent side. length of the opposite side or magnitude of the opposite side is 4. And length of the adjacent side, the side that's adjacent to the angle, is 5. So that comes out to 8/10. This is what we're solving for. So what we're looking for is actually the angle that has this for its tangent, the angle that has 0.8 for its tangent. And to do that, you use the so-called inverse tangent function. If tangent of an angle is 0.8, then the angle itself turns out to be equal to the so-called inverse tangent of 0.8. And your calculator will tell you what the inverse tangent of 0.8 actually is. In this case, it'll be your calculator will tell you that it's about 39 degrees. So this angle here is 39 degrees. And specifically, if you're pointing, say, in the negative x direction, and you rotate counterclockwise by 39 degrees, then you're pointing in the direction of displacement d. So to be absolutely complete about what the direction is, we will say it this way. D is 39 degrees counterclockwise, just write CCW instead of writing out the whole counterclockwise. Counterclockwise from the minus x direction. Minus x direction, rotate 39 degrees counterclockwise, and now you're pointing in the direction of D. And we'll try practicing more of this in class, and then when we start thinking about forces, we will be thinking a great deal about components of forces, and these ideas will come up all the time.